Hello everyone, today I am going to deliver a lecture on flexural design, which is flexural member design, which is beam, girder, joist, purlin or lintel, and flexural design for shear. Okay, also the shear, and this is completely flexural design. So let's start. So before I'm going to the explain the math, now I'll discuss the some theory. Here is the nominal moment capacity of beam section. We have been seeing here the nominal flexural strength is vertical axis and slenderness is x-axis. As the compact section we have been seen here MP Fi into Zx, which is the compact section, and then non-compact section we have been seen here. I am already discussed the compact and non-compact section in previously. So I think you all know the about the compact and non-compact section. Uh, okay, so I'm revising here. Here is the compact and non-compact section. So the definition of non-compact section is a section where the element, flange or web or properties such that carefully develop in their plastic moment capacity without buckling. On the other hand, we can see non-compact section here, a section where the elements are slender enough with the local buckling occur before plastic capacity is reached, but after the yielding of moment. So we have been seen here after the yielding of moment. So non-compact section. Here is a Yemen slender flange in this formula. So we can find out the slenderness ratio by using this formula, and MP we can use this type of formula. Okay. So flexural design consideration. So lateral torsion buckling we have been seen here. The same nominal strength in y-axis and x-axis is the lateral unbraced length LP, LPD, and LR. So here is the also compact section, and MR is given 0.70 Fy(x) and Mn equal to MP, and Mn we have been found in this formula, and also nominal moment, another nominal moment is found here with respect to different lateral unbraced length. Okay, we've been seen here the another formula, or we can find out the LP from this formula. Okay, let's start. So before we starting, we have to memorize some deflection where the support condition. If the pins hinge, then we can deflect delta equal to WL cube in 48 EI. If the load is if the support is fixed, then we can use 1/3 1/3 48, which is 192 WL cube into 192. And we can use if the UDL load is given on the simple supported beam, then 5 WL cube divided by 3488 into EI. If we use the fixed support in both in, then we can multiply 1 by 5 with the previous, and it will be WL cube by 348 384 EI. And if we can see the cantilever and the point load, then it will be WL cube by 3 EI. If we get the moment in the end, then WL square 2 EI, and the UDL load in cantilever, then W into L to the power 4 into 8 EI. So if you memorize this chart, then you can grab the opportunity very fastly. So we can now we are going to the design the flexural member, which is the beam member. This is our first example. So let's read first the question. So select the highest W or M section to carry the uniform distribution dead load 0.2 keep perfect and superimposed. In addition to beam is 2 wire, and the 0.8 keep field live load, and the simple supported span is given 20 feet, and the compression flange of beam is fully supported against lateral movement. So we have to use a ASD method and select the following section: A36 and A992 and A52 grade of 65. So this grade is given, and the figure is also given. If figure is not given, then we can draw the figure with respect from the based on the information. So you've been seen the dead load is 0.2 and the superimposed load also 0.8. It could be it could be floor finishing, it could be something which is superimposed. Okay. So bending moment, we know the WL square by 8. In this way we found 50 kip per feet, and we use the ASD method and found M equal to phi Fy into Zx, and found Zx value of the Zx 27 into 8. So now when we get the Zx value, then we can select a section which value is greater than 27 from AISC manual. So I will get, this is the AISC manual. We have been seen here is the section where section dimension wavelength. So we have to select Zx. This is the x-axis and this is the Zx. So now we are selecting 29.7, which is Zx, which is greater than 27.8. So initially we have been found 29.7 for from this selecting this this type with W 12 into 12 into 22. Okay, so if you get this, then we can get all thickness TW divided by 2 with thickness, flange thickness, and so many things which are needed. So we have been found this from the AISC manual. We can see here TW divided by 2 is 1 by 8. So we have been found B into 2 TW. So B into 2 TW, there is no given, but we can calculate it here. I have been taken the another manual, and BF is given BF. BF is here is a BF is given 4.03 in inches. So 4.03 we have been on. TF equal to is given. So TF we have been seen here the TF equal to 0.425. So 0.425. In this way we can select. We can take in this data from AISC manual, which is the greater than Z value. Okay. So now we check the limit Z, BF equal to 2F into 65 root over 5, and we have been found this compacted limit is satisfied. And step 4, we can use the allowable bearing allowable capacity of the section. We can see here is a we have been used Zx is new Zx. We have been found 29.3, which is taken from AISC manual, and found 52.65, and UDL we can see W into 0.2 into 22 into divided by 100. How will get 22? We are choosing 12 into 22. So this is 22. So it is pound, and we are dividing 100 to converting in kip, and found W value. And now we are trying WL square by 8 and found the moment 51.1. So 51.1 is less than the capacity 52.63. So we can say the design is okay. So therefore our selected member W 12 into 22 is okay. This is our answer. So let's see another example. Here's the design the lightest W section with a 992 steel Fy equal to given, and they achieve the full plastic moment capacity and the load arrangement given in figure. Use the ASD method. So you can see here the dimension and load is given. One is point load is 48 and UTL 1.8. So we can see here for UTL WL square by 8 and point load PL by 4, and found 518 kip per feet. And moment we know Mn equal to Mn. So we are dividing the factor and found 685 by ASD method. Now we check the limit. We check the limit check and use the LB and found 42 into RY. And we see the LB is given 7.2 in the question, and put this value in here, and 7.2 which is 19 inches and 19 inches, and found the RY value is 2.143. So required moment we have been calculating Fy into required Rx, and required Rx into 208 inches square. So we have to select a member whose Zx into 208 inches square greater than 201, and Ry equal to 2.21 feet. So we are going to in the same way as manual, and select the W18 and by 106, and host z value is 203 and ry equal to 2.66. So remember this value, these are this required r in not ry, not r z. So this is the ry. So in this way, sorry, this ry, and this ry, and this is also zx. This is not zy. Okay. So moment will be we can use the self weight and imposed load WL square by 8, and how we'll get the W value. W value is nothing but it's the section weight. We have been found 8 into 106. It is found for pound and divided by 100, so it will be 0.106 for keep, and length is we've been found 30. If we adding all the value, and it will be 30. And in this way we've been found 5 to 9.9 cubic feet. Allowable capacity we've been found 18 into 106. So if we are using the ASD method and putting the alpha value is 0.60, and found 575, which is greater than 529, which is applied load is greater than applied load. So selected beam is W18 into 106 is okay. This is our answer. So you can see another example, which is the select the highest W section is carrying the uniform dead load of 0.0 cubic feet. This is the dead load, and live load 1 cubic per feet, and simple supported in 42 feet. And adequate lateral support is provided, and the live load is deflected. So deflected, we know limit is L by 360, and use the F5 to grade 50 and use the ASD method. So let's see. We know the W equal to dead load plus live load 1.4. As we are using ASD method, if we use the LRD method, then we can use the multiplication factor such as 1.2 dead load plus 1 live load. But we are not using multiplication, as we are using ASD method. And as the simple supported, we know the WL square by 8 is as a moment calculating, and found 331 kip per feet. And we using ASD method Mn equal to 5 Mn into Zx. In this way we found that Zx is 132.4. Now step 2, we can give the allowable deflection limit is given in question L by 36. So L by 36 we can found 1.4 inch square, 1 by 4 inch. And as we know the we have been known the uniform dead load, then it will be WL to the power 4 by 384 EI. This is our allowable limit. We have been found in this formula, W 5WL by here the WL cube by 384 EI. So we have been taken this formula from here, and putting all this value as the simple support, and we are multiplying with 5, and found this is the limitation. This is the limitation, and code value we have been taking from code, and found I equal to 1724. So we have to choose a section whose section is greater than Z value is greater than 132, and the I section is greater than 1724. So we have to go to the in the same way in the AIC manual, and we have to put we have to clarify where is the moment of inertia value, and as well as the Zx value, which is greater than this value. So we have been selecting 21 into 93. If we go to the 21 into 93, then we will find this graph as usually. So 21 into 93, this is the 21 into 93, and Zx value this is our value. So if we 21 into 93, this so we have been found Ix equal to 2070. So Ix equal to 2070, and Zx, so Zx is here, Zx is 221. So Zx equal to 221. In this way we are selecting in this member with respect to the with providing this information. And we now will checking shear by this formula we've been seeing the 53 is greater than the 37, and shear we can see in this way, and phi equal to and found this way, and w equal to have been use del root w times self weight as we have been found 21 into 93, 93 is keep, so we have been providing dividing 100, and it will be keep it is found for pound, and we are dividing 100 to keep provide multi transferring into keep, and b equal to wl by 2 and found 332 so 205 which is found is here. 205 is section and capacity, and the apply share is 335, so is less than the capacity, so the section is okay. So these are section done. So now we'll give the another reverse calculation. This is called beam analysis, or you can say is a flexural member design also. So flexural analysis, you can say determine the design of the bending strength in the moment capacity from W 14 by 74, and flexural member is given this greater than 54 and still continuous lateral support, so LB equal to 0, and unbraced length LB into 15 and CB equal to 1. So as per from this data W 17 as W 14 by 17, so we will go to the W 14 into 74, W 14 into 74, then we have been found all the values W 14 into 74, so this data. So as per providing this data, we will found the area which is 21.8, so area where is area is 21.8. so all these data we have been taken from this AISC menu as per our requirement. Then check the flange and found that 4.31 is less than 9.19, so compacted is flange. So now checking the web, we have been seeing that 25.4 is greater than 90.5, so compacted in web. I will calculate the MP. Here is the MP formula Fy into Zx. We are known the all the value. Zx is taken from here, and moment is also we have been known the all the moment. So there is no problem at all. So Fy, you know the Fy and Zx value have been found 126. In this way we can calculate the section moment. Section moment MP equal to 6300 keep in C, and now we will know the LB equal to 15 and CB equal to 1 given in question. Then we can found the LB which is 8.76. So 8.76 is greater than 15. So as 8.76 is greater than 16, then we can use the LR. We now are using another method, another formula to calculate LR. This formula, and found 31 feet. So you can see LP, which is the found is LP 8.60, and LB we have been given in question 15, and finally we have been found LR 31. So if this sequence is govern this equation, then we can use this formula. If the sequence is not governed, then we can use another formula. So we have been used this formula and found the MP value. MP value have been taken is here Fy into Zx. Fy is given 50 and Zx, so we can calculating. We are founding from this shear from the cement wall. From here is a Zx value which W 14 into 74, W 17 4. So this is the Zx. Zx equal to this line 1 on 5. Okay, so Zx we have been found 126. Okay, 126. Okay, oh sorry, I'm taking the wrong number. 126. This is the Zx value 126. So in this way we are founding the MP and putting MP value and found Mn, and then calculating the nominal moment capacity as per ASD, and this is our last. This is our final result. Now we'll calculating another analysis of beam. Determine the design of the moment capacity of W 14 into 8 to 4 beam section is used to the flexural member in grade 50. For the section beam is shown in given below, and there is no lateral brace and between support A and C, so use ASLRD method. So you can see here the section which is selected to 14 into 64. If we selection, then we can get the all this member. As we know the section capacity, then we can use the all this information, and W 14 into 68, W 14 into 68, 14 into this is the 68, so 61 68, okay. This is the 68 dot in given in red line, and also this is the 68 is given in line, and taking all the value and checking the flange in this formula, and found 6.9 is less than 9.9, so compacted flange, and check the web, we can see 54 is less than 92, and this is compacted, and Fy now MP equal to Fy into Zx. Zx is taken from this formula. We are known that Zx is here almost 115, so 115 is Zx taken from AIC manual, and found MP, and LB is given, and CB is taken the 1, and LP we are taking LP is calculating by this formula, and found 63. As we know, the LP is 8.6, which is where LP is 8.6, and LB equal to 16, so LB equal to 16, and LR equal to 63. As the sequence is maintained, then we can use this formula for MN. Otherwise, we can use another formula. Okay, and found the moment, and the nominal moment have been found here. And if we calculate the moment equal to PL by 4, then we can found the load in back calculation 103 kip. We can use this the load of 103 kip. So let's see another example, which is beam design. Use the ASLRD method approach to determine the maximum uniform distributed load W, and that can be act in the simple supported span in 24 feet, and lateral supported axis is only inch of the span, and the service load is 75% live and 25% dead load, and the section is given 24 into 84. This section is given, of Fy is given also, and assume the moment gradient factor CB is 1. Okay, so note the beam self weight is not neglect, and the hence it must be accounted for. Okay, so if we know that W section M W 24 into 84, then we can go to the AIC manual, and select this member, and found all this data from AIC manual. Now we're checking the as we have been seen the previously. Now I'm not showing again and again. So check the flange, we have been found 5.8 cc, which is greater than less than 9.81, so compacted flange, and the checking web we've been found 54.9 is less than 90.5, so web is compacted. So now we'll, step 3, we can use the calculate the MP, which is Fy is given, and Zx 224, so it will be taken from a similar 224, and found the moment is 11200 kip inch square. So now we are calculating LB, which is given 24 kip, and CB equal to 1, and LP we have been calculating this formula, and found 6.9, and LR calculating in this formula, and found 8.4. So we have been seeing LP is 6.9, so 6.9, and then greater than LB equal to 24, then we have been found 24, and LR is 84. So sequentially, if the formula is sequential, then we can use this formula. Otherwise, we can change this formula as per our graph, and found the moment, which is 102,237 kip, which is less than 1120 kip inch square. So okay, and the nominal moment we can found 9213 kip, and if we use the back calculation WL square by 8, and then we can find the W value 0.88 kip inch square applied. So now we are using W84 pound per feet square, as we have been selecting this W24 into 84, and found 0.007 kip inch square. So W applied into W self weight, we have been found 0.007 kip inch square. Okay, these are the cover the flexural member design. Now we'll show the flexural design only for shear design. Okay, let's see. Here is the shear design. You can see that determine the elastic shear stress distribution on W24 into 94 beam is subjected to the service load in shear 24 kip, and also compute the portion of the shear carried by the flange, and that carried by the web, and figure given in below. So this figure is also given, and the moment of inertia and section is also given. So shear stress as junction and flange and web. So you can see flange and web. So we can use the y bar which has a1. We can divide it the 1, 2, and 3 type of section when divided. A1 y1 a2 y2 plus a3 y3 and divided by a1 a2 plus a3. In this way you can calculate the CG of the y-axis, and which is found 12.125 inches from bottom. This is the from bottom. And qx star which is flange, which is a1 plus y bar. Y bar we have been taken, and the y bar which are 24, we have been known that 24 is the total depth, and minus 0.875 is the flange, and divided by 2. So these are the y stars bar we are taking here. The individual portion we have been taking distance, and tau max tau flange equal to b into q into I into b flange, and found 0.70 ksi flange, and y in respectively we are changing the b value of y. As the flange we can see 9.60 is given, 9.065 and 9.065 opinions. For y we can 0.055 is given in diagram, and found all the value. And stress at the neutral axis we have been using this formula and found 103, and stress at neutral web we have been using the web and found it 18.7, and shear carried by the web. So using Simpson's integration rule, 1/6 into a1 plus an plus 4 into a1 plus odd number into summation of 2 into a2, and found 196. And percent of shear carried by the web we have been seeing 196 is divided by 200 and into 100, and found 98%. So 2%, and remaining 2% will carry the flange. So you can see here the graph is given on 0.76 and 13.36 in 18. Here is 18 in neutral axis, and 13.36 is in two side. We've been found here 13.36, and 0.76 is also found is here in flange. So this is the diagram is found. So average shear stress on web we can see B equal to A, which is A mean D into TW, and found 16. So which is 11, which is 11.6 is below the maximum level. So we can see we can now we can see the another shear design, which determine the elastic shear stress in distribution on W 24 into 94 is given here. The beam is subjected to the surface shear is 200 kip, and also compute the portion of the shear carried by the flange and that carried by one figure given below. So these are the figure below. In section we have been found here. So shear force we have been found 200 is given also questions. So we are finding the CG of the y bar a1 y1 plus a2 y2 plus a3 divided by a1 plus a2 plus a3. In this way we can found the y bar. Otherwise we can, if the given in section, then we can use the manual for getting the y bar also, but we are using the manual calculation. Okay, so now we calculation I, which is section 1, 2, 3 summation of all section I1, I2, I2, 3, which is BDQ by 12 into A1 plus A2, which is A1 into Y1 minus Y bar, and in this way we can calculate the moment of inertia of all the section. So now stress at the junction at the flange and web we can see here is there at the top. So Q star equal to A into Y bar means Y minus Y bar. So big value minus small value we have been found 90.33, and flange tau shear stress in flange so equal to B equal to Q equal to I by Q. So Q have been found in 90.33. This is the important for us. And the web we can found the web value have been used. B value is 1, as we have been seeing the web is B value is given 1, and found 5.32. Stress as the neutral axis, and neutral axis we have been used the flange plus bottom, and we have been used we have found the say 166.8, and neutral axis we have been found BQ by I, and Q is found 166.8 in the very recent, and found 9.3 KSI at neutral axis. So stress at the junction and junction of flange and bottom at the bottom. So we'll calculate now bottom. Q star equal to a plus y minus y star. So first y will be the bigger value, then second y will be the smaller value. So as we know, the section is 1 into 10 into 1. So if we go to the picture, then we can see this is 1 and 10 and this is 1. So we are multiplying both and found 10 into 1. And y we have been found 11.6 and minus 1 by 2 and found 113. For flange we have been found 0.65 and for y we can found 0.64. So now if we calculate, if we draw the diagram, we can see the 6.47 is in y and the 0.65 is the y. We can see y, and the neutral axis we have been from 9.7, so this will be 9.7, and the 5.26 also have been found in y, and the 0.75 is flange. So 0.75 is flange. So shear carried by the y, so using Simpson's integral formula 1 by 6, and we have been found and 2105 KSI. So shear percent of shear carried by the web, we have been found shear in web divided, it will be ratio divided, it will be divided by shear we have been found in design into multiply with 100 and 105. So these are the index. So you can see another extra now we are seeing the extra math. We compute the shape factor of the following section W, and about is the strong axis. So you can see we have been found y bar in y axis a1 y2 a1 y1 a2 y2 plus a3 y3 divided by a1 plus a2 plus a3, and this is the from CG is from bottom, and we have been taking the I value, which is all the section I1 plus I2 I3, and C will be a neutral axis 1.25 into 14 into 2 1.25 we have been founded, and for 14 divided by 2, and it will be 8.35, and section modulus, which is I by C, have been found 3.7, and Z will be b square divided by 4 into b square plus b square into 4 into b square by 4. So b square by 4 equal to a1 y1 plus 2 into neutral axis, and we have been found 284.25. And the shape factor, we know z into z divided by s, we have been found 1.22, which is greater than 1. So it is okay. The shape factor must be greater than 1, or we can use the shape factor is mp equal to ay or z plus s. So if you have any question, then let me know. I will try to convince again you, or I will giving answer, or you can mail me also. Thank you everyone for your patience.